other than to introduce our first speaker and hand over to them. He's been a pioneer of non-reversible sampling algorithms for many years now in statistical physics, and I can't think of a better person to open the workshop. So please put your hands together and welcome Werner Krauth.
So good morning, everybody, and thanks to the organizers and the Isaac Newton Institute for having me come here. Also, thanks for having given me. So we are here at the sampling for the beyond the diffusive regime, and I just pushed out a paper last Tuesday, and the title wasn't right. I had a problem finding a good title, then I looked at where I'm going to talk on Monday. So now I changed it, an appraisal of sampling strategies beyond the diffusive regime. That's what I'm going to talk to you. So thanks again for having me come here. So I'm doing a comparison between, a very well-known method, which is Hamiltonian Monte Carlo, and I compare it to a representative has different names of piecewise deterministic Markov chain, which we call event chain Monte Carlo. And so here are two papers that I will talk about in detail, and then there are two other earlier papers. So just as a historical reminder, this is where we all come from. Paper 1953, Metropolis et al., Markov chain Monte Carlo, introduced the idea of sampling. And if you read the paper, you'll notice that they introduced the detailed balance condition, and they also went beyond the detailed balance condition. But that's a subject that we can discuss later. So Markov chain Monte Carlo, as you know, is absolutely everywhere in science, in engineering, in the social sciences, and as Sam just said, the reversible version of Markov chain Monte Carlo is the original physical foundation and has kept on for decades and more than half a century. So the reversible Markov chain Monte Carlo makes a mapping of a general computing problem onto a physical system in thermal equilibrium. In thermal equilibrium, we have time reversibility. I mean, I'm just talking to you as a physicist, and I excuse myself. I'm just a physicist, so if I'm later on, I'll have unclear math. Then just please interrupt me. So anyway, so reversibility means thermal equilibrium means diffusion. And the local reversible Markov chain, so local, I will discuss that in detail a little later. So as soon as you have a local Markov chain, that means you can only make very small changes, then you are bound to have diffusive motion, and that's slow. It's not true that every reversible algorithm is a slow algorithm. For example, look at the cluster algorithms that have been extremely powerful, but they are non-local. So there are essentially two strategies to overcome slow diffusive motions, one of them being a non-local reversible Markov chain. And I'll treat here the case of Hamiltonian Monte Carlo. And the other one is to have a local but non-reversible Markov chain. And the example I treat here is the case of event chain Monte Carlo. So what I want to do is I want to go through an example of just a model system and just discuss it in as much breadth and depth that I can. And that's the example of the harmonic chain. So the harmonic chain, think of it as just a chain of particles, of n particles sitting on an interval of length L with harmonic springs between them. So you'll see this picture up there several times. And just to have a clear definition of what I mean, I have particles from 0 to n-1, the ring of length L, periodic boundary conditions as I showed here. And I have, in some sense, the first a little subtle point is I take one particle x0 and it's between 0 and L, and the particle x1, x2, or the positions x2, x3, and so on are not necessarily the positions. They are the elongations because they can go around the ring in a small system at least. So I have particles on a ring with periodic boundary conditions, and in the plots I'll show later, L will always be 2n if you want to do some conversion into your own units. Okay, so that's a very simple system. The interaction is the following. So now the painful thing comes in. The interaction is xk minus 1 minus b. So interaction, you understand that the stationary distribution will be e to the minus beta or e to the minus u, the interaction energy. So that's the log of the density. 1/2 sum xk minus 1 minus b squared. And now let's do a little calculation. It's quite early in the morning, but I have done this calculation. You can almost be sure that this calculation is correct. I expand the power, chug, 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 and I have two terms which are constant and which I can drop. Okay? So there is an interaction between particles, but there is an equilibrium distance. So if I just take two particles, xk and xk minus 1, they like to be at position B, and the interaction potential is like that. But as you see, it's just the term B is just a constant, and that's maybe why it has been, or it can be thought of just being unnecessary. But as we will see, this term is crucial for the non-reversible Markov chain that I will discuss with you. And then, of course, what I will also discuss is that the B can be introduced in any interaction potential, because here you just anyway, I will go through it, so it's more general than just the model. So now we can compute Boltzmann rate. So that's the Boltzmann rate, or the stationary distribution, exponential minus beta u. I keep the beta, but then later on I'll set it equals to 1. I can compute the partition function. Takes me a lot of effort. I have to diagonalize the triplets matrix, and then I start really getting sweaty. But we have been able to do that, and compute the pressure. The pressure is the derivative with respect to the system size of log of z, which means it is in physical terms it's the power, it's the force which I push on the boundaries of my system. And the pressure is given by 1 over L plus B minus L over N. And there's a critical pressure where the critical value of B where the pressure goes to 0. So up to a term in 1 over L, the critical B is going to be L over N. So if L is 2N, then it's going to be 2. And that will turn out to be a special point for for event chain Monte Carlo. So here you see, of course, that the partition function also only trivially depends on B. So you may ask, why do we? Anyway, we'll see the story. So now we have sampling algorithms, and of course, although we may be interested in Markov chain Monte Carlo, we actually don't want to do it, right? We want to have a direct sampling algorithm. That's what we actually want. We just want to sample the distribution. So that means we want to sample positions x0 to xn, x1, xn minus 1 with this weight. And if we can do it without running a Markov chain, we'll just be happy people, right? So, for example, we can be happy people because there's an object called the Gaussian bridge, invented by Levy in 1940 in occupied France. Just imagine. So anyway, in this horrible situation, he came up with this algorithm. He said, well, let me put x0 and xn are different by L. And then it just, so I know two positions. Let's sample the intermediate point. 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 And in an effort of O of n, I can output a perfect sample, a direct sample of my probability distribution, which is the Gaussian. Again, this algorithm is, of course, completely independent of B. So why are we so interested in that? Anyway, so we'll see it. So now let me just, I present my apologies for showing this slide, but let me just do it. So there is an object called detailed balance that many people in mathematics and in physics like. In mathematics, you like it because the spectrum of the transition matrix becomes real, and you can do a lot of math that you cannot do in the general case. In physics, we like it because in order to run an algorithm, it's a detailed balance between a configuration x and a configuration x prime. And in order to set up an algorithm, I only have to know x and x prime. I don't have to know the rest of it. So what I'm doing is here the detailed balance condition, you know it. I set it up into an a priori probability to propose the move from x to x prime, and then into a filter. So that's my filter, and it's the filter which is a Boolean random variable, but let's say it corresponds to a Boolean random variable, but it is the decision whether I accept or reject the move. So here in the Metropolis filter, I mean, everybody has known it, and it's just, so let's say the math, mathematicians like to write it like this, physicists like to write it this, but it's just the same thing. So that it just depends on the a priori probability to be symmetric, and then it's a special choice. You say that the pi of x times p of x prime is the minimum of pi of x and pi of x prime. That gives you the Metropolis filter. So the Metropolis filter, here I'm starting the first of 17 algorithms. So that's the Metropolis filter. But I mean, just the point is here, you can actually write it down. So the Metropolis filter is you take you choose your particle k, you make a random move delta from minus delta x from minus delta to delta. Then you compute the change of energy, you evaluate the change of energy, and then with a probability exponential of this thing, you go from x to x prime, xk to xk prime. That's a perfect example of a local algorithm. Why is it a local algorithm? Well, it's a local algorithm by choice, because I just propose to move a single, so here you see the choice, right? I propose to move a single particle. I could, of course, move a whole bunch of particles, but if I move a whole bunch of particles, I fall off the riff of where the stationary distribution is large and the acceptance probability will plummet. So that's what we are all trying to overcome, the imposed locality of our algorithm, which comes from the fact that the proposed move is just a random displacement which knows nothing about the physics of about the mathematics of our system. So that's the Metropolis algorithm, and of course it's independent of B. Why is it independent of B? Because it evaluates differences of the energy, and the differences of the energy all differ by the same value of B. So that's clear. So let's do a detailed balance 2 of 2. You saw it before, it was 1 of 2, now it's 2 of 2. So we move a single particle. So there was not enough space to put my little picture on. Excuse me, there was not enough space to put this thing here. So, but you see, you have it in your mind. We have a chain with harmonic springs, but it's special harmonic springs, right? It's harmonic springs that are, the interaction is in xk plus 1 minus xk minus b square. It's not the absolute value of this minus b square. So it's a sign difference between the two. So anyway, so you try to move your particle, you evaluate the changes and so on, and then you go on. So now let's cut it up into smaller pieces. So the initial particle k had an interaction with k plus, which is the uk plus, it has an interaction with K minus, which is the UK minus. And from the UK plus and UK minus, you get to UK plus prime and UK plus minus. UK prime minus. So the metropolis filter that we just discussed, and it has been discussed in zillions of papers, is this one. So I compute the minimum of 1 exponential of minus change plus and change minus. That means you evaluate the change of the energies and then you go where you want to go. You understand? So now I can make a little change. I can make a little change and use another filter, remaining completely in the realm of reversible algorithms. So I can use a factorized filter. The factorized filter, instead of computing the change of plus and minus, it does the following. It is the filter of the minimum exponential of minus plus term of a factor. We call this a factor. So there is the plus factor. So when I'm moving the particle, it is in contact with two factors, the plus factor and the minus factor. And I can make a metropolis decision on the plus factor and on the minus factor separately. Okay? It's really simple. So now, of course, I can do the same thing as before. I could take a random variable and check it with respect to this term here, and accept if it's smaller than 3. But that's not a very clever, not a very good idea. A much better idea is the following. I take 2 random variables, one that checks for the plus factor, and another random variable that checks for the minus factor. That's a perfectly useless algorithm, because you do a little bit of calculation on the back of your piece of paper that you get from the Isaac Newton Institute, and you get that you find out immediately that the acceptance probability of this factorized filter must be smaller or equal than the acceptance probability. So you throw it out, but that's not. Sometimes you have to overcome things. So let me do the following. So this is the factorized metropolis algorithm, algorithm 2 of 17. So the way it goes is the following. I propose a move forward or backward of k. Okay? I check the change of the stationary rate of this factor, Jack, UK plus, and I compute the change of the stationary rate of the minus factor. And then what I have to do is I have to check this thing here, minimum of this, so I compute this term and they compute this term. And then I take a first random variable and see whether this one accepts it, and I take the second random variable to see whether this one is accepted. And I accept the whole thing only if both of them accept. So here you see it. I have a random variable plus, or random number plus, random number minus. I check whether the first factor accepts the move. I check whether the second factor accepts the move. And only if both of them agree, the committee here agrees, then I accept the move and output the thing. So this creates sometimes a little bit of confusion. So we wrote a very easy-going algorithm, maybe not for you, but for easy-going paper in American Journal of Physics, just to explain that for example, that making this decision doesn't mean that these two factors are independent. That's complete. So anyway, so people get very easily confused. So we try to. But it's a diffusive algorithm, and it's not going to be any better than the previous algorithm. It's going to be even worse. But it's the starting point of a later story. So now, let me do Hamiltonian Monte Carlo. So Hamiltonian Monte Carlo, in fact, I have known it since 1987. 1987, first time I was in the UK, in Scotland, at the summer school. And at that summer school, Twain, Kennedy, Pennant, they were all there, and they presented a little algorithm. It has been a complete blockbuster for the field of lattice gauge theory. and has been used in lattice gauge theory. It has completely, it has completely replaced all other algorithms. And so it was kind of funny. At that summer school, all the old people were presenting their algorithms and telling us what we should do to further their fame and so on and so on. And then there were these postdocs presenting their algorithm, and they had this smile on the face, and they of course knew that they were doing something very interesting. So the interesting thing is, you add the additional variables. So you go from x you go to x and x and p. You all know this. You go from the distribution function pi of x to a distribution function pi of x and p by adding momenta. So then, ideally, in time, when you propagate this in time, you conserve the energy. But when time is discretized, you simulate what's called, I think, what is called a shadow Hamiltonian. It may or may not exist. Really, in the example that I'm showing, the shadow Hamiltonian actually exists. So you simulate a system in discrete time, but it's no longer the system you want to simulate. But then you evaluate the gradient of u. So the gradient of u gives you the momentum, and the momentum gives you the change of v. So that's the basic idea of Hamiltonian Monte Carlo. It has become extremely popular in the last 15 years. Something that I found out just this year how popular really it is. So here again, algorithm number 3, that's the Hamiltonian Monte Carlo for our system. So you go from time t to time t to time t plus tau. You make this evolution. This evolution, unfortunately, is not the evolution of the Hamiltonian that you actually want. You discretize it, and you think you always have to discretize these Hamiltonians. So you discretize and you make a mistake. You make this mistake in such a way that it's perfectly reversible, and that you can go from x to x prime, and from x prime to x with the same on the same dynamical manifold if you want to. So you have a what we call a non-reversible algorithm to get from x to x prime. But then you reversibilize the thing, and you are back to diffusive. You are back to reversible Monte Carlo, but at least you're not in a local diffusive Monte Carlo algorithm. So let's see the following. So there has been tons of papers that I'm trying to understand, and maybe I will understand better. So it's the stability. But let's say if you don't understand, we just do a little simulation, and the simulation shows you that Hamiltonian Monte Carlo does something fantastic. It makes a move which is not just a little delta that we had before. We had a little delta in the Metropolis algorithm. It makes a big move, a big move, a big move. And here I show what is the acceptance probability of our algorithm. Here n equals 64, so I have 64 particles on my system of length 128, whatever. And then I check, I can go, so I have a number of iterations. So that's my number of iterations, iota from 0 to I. So I make this move, delta, I make this move of epsilon, 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 make it more and more and more and more. And with the old science, with Monte Carlo, with Metropolis Monte Carlo, the probability to accept would go down. But here you see, I can do 7 moves, n over half moves, n moves, 2 n moves, 4 n moves, 8 n moves, 16. So this is a little special for the harmonic model because the shadow Hamiltonian actually exists. But it shows you can make moves as long as you want, and you will keep a good acceptance probability. That's really fantastic. What is not so fantastic is that you have to choose a small epsilon, a small step size. And in this example, it's very clear that the epsilon that you have to choose goes like 1 over n to 1/4. And from my discussion with colleagues, I understand that this 1 over n to the 1/4 is well understood theoretically. If you have a better solution, just I can revise my paper and I'll put that in. So what it means is the algorithm allows you to make a number of iterations I times epsilon, which is much larger than the 1. It can be of the order of n. And even in the general case, it can be quite large. In quantum field theory, it can be quite large. So the algorithm is non-local. That's one thing I wanted to. But then at the end, because we are simulating the shadow Hamiltonian, not the real one, we have to do the reversibility. And this non-locality is costly because you are constrained by the epsilon that you can take in order to avoid this instability where you go to an acceptance probability, which is just enormous. So now let me show, I showed you I'm doing the appraisal of two different ways of overcoming local reversible, the problems of local reversibility. So I'm showing you event chain Monte Carlo. So event chain Monte Carlo derives, as I told you, from the factorized metropolis algorithm. Factorized metropolis algorithm, again, it was, I have a K, I propose the move, and it has to be accepted by this factor, it has to be accepted by that factor. Now let's do the same thing, but let's only make forward moves. The algorithm becomes non-reversible, and you have to do a little bit of mathematics. I'll do that at the very end if I'm not too late. So I do that at the very end. So you only do forward moves. You also do only infinitesimal moves. Excuse me for my language, but infinitesimal moves, you go from Markov chain to Markov process. In my humble opinion, as a physicist, there's not so much of a difference. I mean, for this example, there's not so much of a difference between a Markov chain and a Markov process. So I can make it into, I take epsilon small and dt, and so you know how physicists do differential calculus, and I think I get along quite well. So we do infinitesimal moves. So the point of the infinitesimal move is the following. So here is k, here's k minus 1, here's k plus 1, and I'm making an infinitesimal move only forward. And this infinitesimal move will almost always be accepted because it's infinitesimal, and my energy, let's say my stationary distribution is, how do you say, differentiable, or I mean just moves little when I move little, right? So little makes a little change. So I move little makes a little change, and then what happens is that the move will, in the previous case, the move could be rejected by both factors. But now it's either rejected by the plus factor or by the minus factor. And then I have the third change here, which is that the move is persistent. And persistent means that if it's rejected by the plus factor, then next time, so if it's not rejected, then the same particle moves again. If it's rejected by the plus factor, then next time this guy takes over. Now it wins the election, so that he's going to be the boss, or she. And if it's the minus factor, then it's the minus factor, which k minus 1, which will be the next move. To make this completely explicit, here is the algorithm. I have it on my website. It's just 20 lines. It's just 20. I mean, it's 15 lines or 20 lines. So the way it's the following: I propose an infinitesimal move of k. And this infinitesimal move is between k plus and k minus. But then you understand that, I mean, there has been, that is, major, of course, then you understand that you don't have to do an infinitesimal move on the computer by putting the delta t equal to 10 to the minus 7 and check. What you can do is you can check, you can move forward, move forward, move forward, move forward. So what I'm going to do is the following. So I'm doing a little calculation. And I have an event-driven formulation written up in these 20 lines, and it comes up with the xk. So the way it goes is I have xk here, I have xk plus 1 here. Let's say the potential that xk sees in xk minus 1 is the following. So it starts here, it will move here. If it's only for this factor, it will move here because the energy goes down, the stationary distribution goes up, or the factor weight goes up, I move up. So that's this z plus. Then I have a z minus, and then I'm going to move up. But then, of course, you can understand that I can do an event-driven formulation. I go up and I go up. I sample a random variable, and it tells me at which point this factor will reject the move. So one move is going to be O of 1. That's the one move from one particle moving, k moving, tack, 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 moving, and then later on k plus 1 moving or k minus 1 moving is going to be O of 1 from from event to event. So that's the algorithm. So now let us do the following. Let's realize that all three algorithms that I presented to you, have parameters. And if I set the parameters wrongly, then I'm not going to be a big winner in this field, right? I understand that. So what are the parameters? The parameters of the Metropolis algorithm has been much discussed. It's this delta x. And how should we choose the rejection rate of the Metropolis algorithm? I don't want to ask those people who have not written a paper on this to raise their arms, because nobody would raise it. So I have, I've been guilty of this, trying to. I mean, in the old days, I've been guilty of trying to find what is the, usually, so there's the famous, for example, there's the famous 1/2 rule, where it's famous and wrong, and then there can be papers can be written and so on and so on. So how do you choose delta? But it's clear if you choose delta equals to plus infinity, then the rejection rate activity will be strictly 0. It's even exponentially bad in delta. So you have to choose delta. So I haven't shown it here. But HMC, Hamiltonian Monte Carlo, also has a parameter. Two parameters. One parameter is, so you start at x, you make epsilon, 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 epsilon. You make them I for iteration. You have a certain number of iterations. And then you have an epsilon. So there are two parameters that you have to optimize. And ECMC, eventually Monte Carlo, has one parameter, which is the B, the equilibrium pair distance. So here is a picture here. This is HMC, and this is ECMC. And the ink here, I shouldn't touch it because the ink is still wet. Because I always do the calculations, and then we have done this before, and then anyway. So so here is so here we have some kind of observable which allows us to check whether we are in equilibrium. We can compute the autocorrelation time. I don't want to go into detail. It's the structure factor of autocorrelation. We can discuss it over what remains of the cookies. So I have some kind of poor man's way of computing the autocorrelation time, and I compute that as a function of epsilon times I. Let's just write it down here because it's a little small. Epsilon. So this is the length of the step that I'm taking. The length of the step, the length of the whole chain that I'm taking from x to x prime. And what I see here is that I reach 1. What it means is that the algorithm and the model is sufficiently simple. It's not completely simple, but it's sufficiently simple that if I do Hamiltonian Monte Carlo, I go from x to an essentially unrelated point x prime. That's what I'm showing here. If I take epsilon to 0, then Hamiltonian dynamics is able to get to another point. Then I resample the momenta. So I get it's really is a non-local algorithm. Second point I show on this picture here is now I go up from very small epsilon to larger epsilons, and I multiply this with epsilon. So of course, if I have a rejection rate of or an acceptance rate of 10%, then not every chain is going to get me from x to x prime, because 90% of the chains are going to be rejected, and I stay where I am. So I correct for this mistake, and I check that I still stay there. So I will have rejections which will move. Most of them will be rejected, but those that get accepted get me from x to x prime, which is essentially uncorrelated. So again, I stay at this 1. So this is fantastic, but of course, so I get convergence in one step, but of course this one step is very costly, and I'll show you that it will cost n square. It will cost n square operations. In fact, it costs n square times n to the 1/4 of operations to get me to equilibrium. And here I show you oh, excuse me, still wet. So here's the ECMC, but we have done that before in the paper I showed before with Zille and Tony Marks. We did this calculation, and we compute the autocorrelation time, the Pullman's version of autocorrelation time as a function of B, equilibrium pair distance. And we see a precipitous drop for B equals to B critical, where the pressure goes to 0. So this is a logarithmic scale. And if I choose B correctly, then the algorithm is going to be orders of magnitude faster than if I choose B, if I have an unadjusted value of B. So now, let me compute, so this is kind of the end of what I wanted to show is the autocorrelation time of the structure factor. So here we have, I'm pitting against each other, Metropolis algorithm, unadjusted eventual Monte Carlo, Hamiltonian Monte Carlo with an epsilon proportional to n-1/4, well-adjusted ECMC at the point B at which the pressure goes to 0, and some other version that I'll show you in 2 seconds. So one is the n-cube behavior, very well understood theoretically, and even proven in discrete models. So we can prove there's nothing we can say. So it's n. We need n cubes, and I'm counting time steps on a serial computer. So this n cube means n square sweeps, and this n square means the dynamical exponent of the system for the physicist means that the dynamical exponent is equal to mu equals to 2. So with respect to that Hamiltonian Monte Carlo, which are the crosses here, the Hamiltonian Monte Carlo does much better. So this is unadjusted eventual Monte Carlo, but compared to this, Hamiltonian Monte Carlo does much better. It has a rate of n to the n-4. So it is only one step from x to x prime, but this one step costs me n to the 9/4. And here is the well-adjusted eventual Monte Carlo, which goes with n to the 3/2. I'll discuss a little later if Michael leaves me the time. I'll discuss that this limit is the optimal limit that we can reach because what is hiding behind it is the whole theory of lifted Markov chains. And they tell you that you can go only from n cube. I'm giving you the physicist version. You can only go from n cube to n cube over 2. There's not much more that you can do. So that's what we are doing. So now, let's do the fine-tuning. So let me give you this little slide here. So the fine-tuning, where does it come from that there is a critical factor? There's a critical B. How can we understand that? And the way we can understand it is through a formula that in our little group, when you were in Paris, we would call that's the fabulous formula. Right? We call that the fabulous formula, which is you can look at, so at some point, you only look at the pointer. So at this moment, the pointer is at this position xk. Then it moves forward infinitesimally, but then it can either jump to xk plus 1 or it jumps to xk minus 1. If you want to, I can show you again the algorithm where it is. You understand? So you rest on the pointer as long as the move is accepted. The pointer remains there, but then if it's rejected by this guy, the pointer moves here, and it's this guy that's moving forward. If it's rejected by this guy, then the pointer goes back, and it moves. And it's really marvelous that an estimator of the pressure of this derivative of the partition function is given by the speed, the expectation of the speed of the pointer. For the harmonic chain, Vx is equal to this formula. We had it before. I deduce it from what I had before because I know P. P is B plus 1 over L plus 1 over the density, where the density is N over L. So this is 1 over density times B minus a critical B. Now I can make two completely trivial, one is completely trivial conclusion. I look at this formula, and it's a trivial formula. It tells me that the pointer velocity, the mean pointer velocity is linear in B, hitting 0 at B critical. You don't have to have gone to university to be able to write this equation. Like it's just that. But what's more interesting is that if you are at B critical, B critical is on the order of 1 over the density, then you can use the same equation. Then if the density is higher, the local coarse grain density is higher than the one that you want to have, then it turns out that the speed is going to be faster. So we have a little formula with my colleagues, and the formula says that the speed is 1 over the local density times the difference of the density. So now we are in equilibrium, or not in equilibrium, we are in some configuration, and the density rho as a function of x is this. Excuse me, this is not 0. 0 is here. So that's the local density, the coarse grain density. So now what's going to happen is, and let's say this is the density n over L. If I have adjusted B to the critical value, what is going to happen is, in this area, the pointer is going to move forward. In this area, the pointer is going to move backward. This leads to a self-trapping of the pointer to even out the density fluctuation, and this explains.
Is this the expected velocity of the location of the active particle at the pointer?
I'm defining the pointer as the position of the pointer. So it changes k. It moves continuously, then it jumps around, then it moves continuously, then it jumps, then it moves, then it jumps. I think that I can still define an expectation of the speed. So then the thing is self-trapping, and this self-trapping immediately gives you why we should expect the n to the 3/2. So there is going to be fluctuations. Anyway, so let me continue. So now let us go into the exposition of something, alternative ECMC. You notice that I wrote this equation. And we have been spending time on this first. This is supposed to be red. Spend a lot of effort making it into red. Is it red? I'm colorblind, so I just cannot see. Anyway, so it is red. So that's what we did, right? That's what we did. But then there are other representations. For example, there's this representation that I wrote in the middle. Okay, I wrote this equation in the middle. Let me see. I think I have still one here. So then I wrote this equation. So we can use this equation, and we had this thing that here the two factors so the two factors, which means if I have k, the k comes in two terms here. It's in k plus 1, and in k minus 1, or k minus and k plus. So now let's do. So this is now under your control. The second line should be red. I don't really see that, but anyway, so it is red. So now you see here that the k comes into 4 factors. So it's the harmonic k plus 1, harmonic k minus 1, and then I have some kind of crummy linear term, k and k minus 1. So I have an algorithm that it's number 17 already. Time's going fast. So anyway, so I have an algorithm, next slide, that shows that this algorithm, and this algorithm has this other behavior also in n to the 3/2. It has the same critical B, but then of course, the algorithm is the following. I'm moving k, and now I have 4 factors, you understand? So the harmonic factor 1, harmonic factor 2, linear factor 1, linear factor 2, and they all have to agree. Goodness, but for example, when we work together, we get so much into factors that sometimes we have a zillion factors, and all of them have to accept. And then we actually program this thing, right? We program this. We have millions of factors, and we can still go by. And we can use it for any potential, for example, hard spheres. So let's replace here the harmonic term, in this thing here, the harmonic term through a hard sphere interaction. So what is now happening is this particle moves forward in continuous time. Chug, 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 continuous time. And the hard sphere term will only protest when k is bumping into k plus 1. The hard sphere term will not complain at all if I'm moving from k with k minus 1 because it will never collide. But then you see there's a little string here. It's no longer a quadratic string, it's only a linear string. And this linear string between k minus 1 and k is going to be stretched and stretched and stretched, increasing the local energy. And at some point, k minus 1 will say, I've had enough, I reject the move. And then what you say, well, I give up. I was the active particle, I was the pointer, and let's move this particle. You understand the algorithm? I mean, I can spend essentially infinite time explaining this thing. So we can, again, we have a parameter b. The parameter b is a control parameter. You understand that this term here sums up to b times L. But in our algorithm, it actually works. It actually has a function. It stretches the string between the particle k that's moving and the previous guy that is there. At some point, the stretch will be too much, and it will say, let me go, let me. So that's the hard sphere thing. So that's the algorithm. It's getting a little stuff. So let's do it in a simpler model. Even the model was already simple, but let's do it in a simple model. And the simple model, I don't want to give another talk on this, what we call lifted tacet. It's just a discrete model. So this is a hard sphere model with these little strings attached to it. And on the lattice, we can model this thing the following way. So this is a hard sphere model. I am doing what I said. I have persistent motion. So as long as the move is not rejected, I move the same particle. So there's one particle which is the active particle, and it moves chuck, 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 chuck. It moves. It's always the same particle that moves forward. When there is a rejection, as you see here, for example here, when there is a rejection, then the pointer moves forward. You see that? So you move from here. You want to move this particle, but it cannot, so then the pointer moves forward. And then with a certain probability alpha, which replaces the b that I had before, I move forward with probability 1, and then with probability alpha, I take the pointer forward. That's the lifted tacet. Totally asymmetric, simple exclusion process. There's a whole story to it. It's a lifting of a lifting. It's not a mistake. It's a lifting of the symmetric simple exclusion process. Has an alpha critical, and it's integrable by Bethe ansatz. So it means that we can write down, I mean, again, physicists as we are, we work with Fabian Esler from Oxford. So we are just physicists. So we have this for 500, n equals to 500, we have transition matrices of 1 zillion by 1 zillion, and we can get eigenvalues exactly to 20 digits. So we are very happy. So now let me show you. So that's just to show you that these algorithms are not completely crazy. So let's take this thing here. You can take this slide. We can discuss it later. And now we write down the transition matrix of this object. You understand that the transition matrix from time t to time t plus 1 is a big matrix, and per row it has exactly 2 non-zero elements. One is alpha, one is beta. Beta is 1 minus alpha. Okay. So there's 2 elements. So now, and this I write that down. So that's a transition matrix for 2 particles on n equals to 4. And it has alpha, beta. And you notice one thing. It's a doubly stochastic transition matrix. So it has a uniform weight. It has non-zero diagonal elements. So it satisfies all the conditions for having a hard sphere density, stationary distribution. It has a uniform hard sphere stationary distribution. So now I'm coming to my second talk. So I just wanted to make an announcement saying that so this ECMC event chain Monte Carlo in a discrete case where it's called lifted totally asymmetric simple exclusion process over the harmonic model has a very deep relation with theory. So this n to the 3/2 scaling for pointer motion is natural. It's just completely natural, like we can understand it. But then you can go much farther. You have a mapping of the pointer motion of the scaling function of the pointer model. I don't go into details. Scaling onto the totally self-avoiding random walk. And that was discovered this year by Tony Marks and has written a fantastic paper, both for the harmonic and for the hard sphere, that means for the totally asymmetric case. And of course, the totally self-avoiding random walk has been introduced by our colleague here, presented by Balin Todt, and the comparison comes from this paper with Laure Dumas and Krauth. So there is a lot of theory behind there that just waits to be explored. The n to the 3/2 is completely natural. I must say that in our Bethe-Ansatz solution, we have evidence for one state, we don't understand it yet, which has a scaling which goes not to like n to the 3/2, but n to the square. So there must be one state that we don't understand yet, but it will come out. So the conclusion, both of these methods that I showed are beyond the diffusive regime. Hamiltonian Monte Carlo is O of n fourth for the one-dimensional particle models. I would be very interested in discussing with you whether we can get this down, whether in this model there's a better way. But I don't see a way of doing it because whatever you do, you evaluate the gradient. If you evaluate the gradient, this essential parameter B is out. So we don't evaluate the gradient, and we have this n to the 3/2. It is consensus-driven, does not evaluate gradients, does not evaluate energies, completely different. But it's a completely general method, and we use it in our daily work. We use it in applications of chemical physics. We use it in real-life applications, and this framework that I showed can be generalized very largely. So the outlook is, of course, we have non-diffusive sampling of a stationary distribution here with a local algorithm that knows nothing about global properties and makes local moves. But at a difference of HMC, it never gets out of equilibrium. I mean, it's completely out of equilibrium, but it always stays in the stationary distribution. There is no discretization error because it doesn't discretize time. It's event-driven, just like argument. So the other point that is hiding that I haven't had time here is that it allows you to sample the stationary distribution without evaluating the log density. So we don't evaluate U. I mean, you see it only hidden behind it. So, but what we are doing here is we are not evaluating U, because if we were evaluating U, then we would evaluate differences of U, and then the B term would drop out. We don't evaluate it. There's no reason why we have to evaluate a stationary a function pi in order to sample it. So we don't evaluate, and that of course gives us applications in chemical physics where the evaluation of the energy is a big problem. For example, if you have Coulomb interactions, you move one particle, it's just a complete nightmare. And books and schools and summer schools and I months have been, workshops have been held on how do you evaluate the energy. Now, of course, we tell people, well, we don't evaluate the energy, sorry. But then they say, well, how do you know that you are right? They say, well, it's by mathematics. And they say, well, you are not a mathematician. I cannot trust you. So then we come up with these simple models. And here, mathematicians, here you agree that the stationary distribution is exactly the one that we told everybody that it would be anyway. So with this, and with this final quote to our chairman, Michael Faulkner was first also of the first paper where we actually put into practice this thing of evaluating very complicated water molecules moving through space, thousands of water molecules. The energy is Lennard-Jones energy plus Coulomb energy plus harmonic energy plus this energy plus that energy. We sample it, and then you say, well, that's the sample. And again, people ask, what's the energy? I say, we don't know. And then, it goes on. Anyway, so with this, I thank you for the attention. I'm looking forward to a fantastic week here. I'll be here until Friday night.
A great talk and a great start to the meeting. Does anyone have any questions?
Yes, about what you said at the end when you said that you don't evaluate gradients, and if you were, you wouldn't have B. But if you use your second representation with the linear part, that would be adding some constant drift to the gradient. And so it looks like to be related to the methods where you start from something even in continuous time ideal. Then when you start with some reversible dynamics and you add a deterministic transport term, transport drift, which is either you try to make it to keep invariant the correct distribution, or you correct it with this non-reversible acceptance part. So do you?
Well, I mean, you know, we are here the whole week. We can, you know, as I said, I'm ready to go from 17 algorithms to 18 to 19. Let's see. So these algorithms, of course, you have understood, have absolutely no rejection. Right? You move, you move, you move. If you have a quasi-rejection, then you move the pointer, so these algorithms have no rejection. But, so I'm, of course, you know, we put out this model just to see whether this n to the 3/2 can be recovered by other algorithms. I would be very interested. I mean, you know, I don't think we have a monopoly on it, but I'm just saying that the regular, what I learned from Bradford Neal, you know, big review, and what people have told me, I benefited enormously from discussions with my colleagues at Flatiron Institute, and that's the algorithm that I coded here was the one that everybody is using. Maybe we can do better, but I would say, let's watch out. Anyway, okay, we'll see.
You have a question? You put your hand up earlier. No. You had a question. Go on, Rob.
So I'm trying to understand the business that you don't evaluate the energy and you don't evaluate gradients. So you must evaluate something about the potential when you evaluate these factors. So could you just say 2 more words about how the actual potential, the real potential, enters the calculation?
I do evaluate. Let's say I do evaluate. It depends on whether you want the whole story or just a small part of it. If you want only a small part of it, I have a particle that's moving, let's say, or I have some part of the system that's moving, and that is in contact with the zillion factors. And these zillion factors, I don't evaluate them. Usually we have an upper bound, we have some bounds so that we don't have to evaluate them. But at some point, somebody says maybe there is the move of particle k that is going, or factor k, it's more general than particles, but let's say, maybe the move of particle k is rejected by particle k plus 1. If that is proposed by the bounding process, it's a thinning process that we actually set up. If that is proposed, then I have to evaluate the pair interaction between these 2 particles. Then I have to, so I don't evaluate the whole gradient, I only evaluate the pair between these 2 particles.
I see, so you just need to evaluate a few pairwise energies each time step.
One pairwise, all of one, even if I have, so for example, in our Coulomb interactions, we have 10 to the 12 factors, 10 to the 6 factors change at each time step. Of these 10 to the 6 factors, 10 to the 6 minus 1 are bounded and treated through thinning. All of it is exact, no approximation made. And then when there is what we call a candidate event, right? When we have a candidate event, then we have just to compute 1 factor energy.
Thank you.
Yes, Rick, one more.
So with the pressure, is it exact for all dimensions if you computed it in 2D, 3D? Like, is it always going to be exact?
Oh, thanks for the question. I forgot to say that. Of course, we don't, I mean, if you knew the pressure, then we could write the paper without doing, if I knew the pressure of the water system, this, then, I mean, it's the basic of, so I don't know, usually I don't know the pressure.
No, but in terms of the mean.
But then the way we do it reverse engineering wise. We don't know the pressure, but then we check that our pointer doesn't move, doesn't have a drift. So we tune the pointer to having 0 drift. And that's what we, for example, we use that in, we use that in higher dimensional systems where we have no idea of the, And then, for example, this pressure estimator of the velocity. So even in simulation, for example, now we are so much into this estimator that even if we have simulations that don't run with eventually Monte Carlo or not with then we put it in there because that's so then we compute the drift of the pointer, and this gives us the pressure much better precision than any other method. So we do it with the reverse way. Thanks for the question. I should have mentioned that.
Probably it's time for a coffee break now. So if we thank Werner once more for a really nice talk.